All right, here we go. Thanks, Dalton, on this exciting article. This is going to be a big article, so I hope everyone sat down and strapped in. Apparently, it's a 62-minute read. Okay, but you know me. Hey, you know me. I like them data structures and algorithms. So this makes me very excited. This makes me very just hot and bothered and all those things all together. All right, in this post, we'll implement a static search tree, an S+ tree. I've never even heard of one of these. Okay, I'm all about. Hey, you know me. I could implement binary search on an array in 5 minutes. That quick. I'm that confident I know the binary searches. So this seems very exciting. I just don't understand how a static search tree ever beats a binary search array. All right. For high throughput searching of sorting data, as introduced by Algorithmica, we'll mostly take the code presented there as a starting point and optimize it to its limits. For a large part, I'm simply taking future work ideas of that post and implementing them. And then there will be a bunch of looking at assembly code to shave off all the instructions we can. Now, okay, so by the way, when they say the phrase premature optimization is the root of all evil, this is what is meant by that phrase right there. That phrase right there. Okay? You do not need to shave off assembly instructions until you're at the end. Okay? Now, since he's just at the very, very end, yes, one would assume that it's okay. Lastly, there will be one big addition to optimize throughput, batching. All source code, including benchmarks and plotting, is coded at right here. Ragnar Groot core camp. Suffix array searching. Damn. Okay. All right, problem set. Input. A sorted list of n 32-bit unsigned integers. Vals. Vec. Oh gosh, bros, we're already rusting. We're already rusted out of our mind at this moment. Can you believe this? We've already somehow rewritten it in Rust, and we haven't even started. We haven't even written, and we're already in Rust. Output, a data structure that supports queries Q, returning the smallest element of vals, that is at least Q, or U32 max, if no such element exists. Oh, interesting. Okay, so you're going to go with the most max value of no element. Okay, that's a weird sentinel value to return. Oh, I guess if you do unsigned, because normally what you do is for signed, you do signed integers, and then you do -1 for index of, like index of, it's not there. Okay, whatever, that's fine. Metric, we optimize throughput. Okay, interesting. That is the number of independent queries that can be answered per second. Oh, interesting. So it's not necessarily latency of query, it's throughput of query. Are we gaming it, boys? Boys, are we gaming it? I just turned into Randy again. I can't help it. Once we start talking about Randy, I start turning into Randy. The typical case is where we have sufficiently long queries as input and return corresponding answers. Okay, note that we will report reciprocal throughput as ns/query or just ns. Is that nanoseconds per query instead of queries per second? You can think of the amortized, not average time spent per query. Okay, I think I see what's happening. So in other words, because there's some things that are kind of given away so far in this article right off the rip. And so one thing they said is that throughput. So throughput you can measure over a long period of time, meaning that if you have some sort of a query that takes a long time for a moment, it doesn't matter. You kind of get rid of all of that. Instead, you just say, hey, we were able to do, say, 3 per second instead of what we expected to be, say, 2.5 or something like that, right? And so there we go. So even if there's some sort of large moment, it doesn't matter because it's just about throughput. And they also said something about batching. So my guess is that by batching, you have, say, a bunch of queries coming in right here, and then you batch them all together and do it right here. So even though this one had to, say, wait the longest, this one right here had to wait the longest, it doesn't matter about its latency. It just matters that you were able to do this many in a second versus something else. That's what I assume is going on here. So forgive me if I am wrong here. Note that we'll be using, let's see, hold on. Benchmarking setup. For now, we'll assume that both the input and queries are simple, uniform, random, sampled 31-bit integers. Why 31? You're already using U32s. In code, this can be modeled like this. Trait, search index. Oh, damn, we're already in traits. Search index, query 1, self query 32, self query this thing. Then we have a query, queryous Betsy with a slice of 32s, queries iter map q self collect. Okay, hold on, I'm trying to understand this here for a second. In terms of, okay, 2 functions with default implementations in terms of each other. I'm very confused by what's happening here because query 1 calls self-query. Self-query calls queries iterator, which maps over the queries and then calls query 1. Doesn't that just keep on going? Am I stupid, or does that just keep on going? Already lost. Brother, I have already lost 9 lines of Rust code. Already don't know what is going on. It happens. I'm a little bit confused as to what's going on here. But that seems exciting, because it seems like you take this and you just keep on calling itself over and over and over again. All right, motivation. Lost on aisle 9, dude. Let's just say, because what I see here, so if you call query 1 and you pass and say 69, it will take 69 and turn it into a slice and query upon that slice and then grab out the first answer. Upon that slice, it's going to go iterate across this slice of 1. It's going to map that slice of 1 with a reference, or effectively dereferencing whatever this value is, and then it's going to call itself again with that 1, which that 1 will then turn into a slice of 1, which will then call into query, which query will then map over, which will then call itself as 1, and then it'll call back in here, and then it'll call back in. Okay, whatever. It does not matter. Aside from doing this project just for fun of it, there is some higher goal. One of the big goals of bioinformatics is to make efficient data structures to index DNA. Say a single human genome, 3 billion base pair characters, or even a bunch of them. One such data structure is a suffix array that sorts the suffixes of the input string. Classically, one can find the locations where a string occurs by binary searching the suffix array. This project is the first step towards speeding up the suffix array search. Also note that we indeed assume that the input data is static, since usually we use a fixed reference genome. Okay, I mean, I think that's pretty fair. Static seems pretty fair. This is why I'm so confused by this, because wouldn't searching over an array better than anything to do with a tree? Unless if the tree is stored in the array? Yeah. Okay, like a heap. Okay, because if you don't do that, right? Because if you do it in an array, you get this magical ability to have all of your memory like in one big old contiguous chunk. Whereas if you do it in an array, if you do it as in a tree, then you get like this whole heap problem, right? And practically speaking, this tends to be a lot faster in a lot of cases than this. But I guess there probably does come a point where this is no longer faster, and this is faster under some set of things. We'll see. All right, anyways, the classical solution to this problem is a binary search. We will briefly visit in the next section. A great paper on this and search layouts is Array Layouts for Comparison-Based Searching by, Kong and Morin. Okay, cool. This post will focus on the S+ trees as introduced by Algorithmica in the follow post, static B trees. In the rest of my time, I will mostly assume that you're familiar with that post. I think we're mostly familiar. For those that don't know what a static B tree is, I don't know what a static B tree is. I assume it's just a B tree that you can't do inserts or removes. But if you don't know what a B tree is, a B tree is really, really simple. So let's just pretend it's just an n-ary search tree. Instead of a binary search tree, it's an n-ary search tree. So let's just say you have the following. Let's just say you have 3, 17, 69. Nice. That means you have 3 slots, and that means you could have over here, you have up to 4 children. And so all of these elements are less than 3. All of these elements are greater than or equal to 3 and less than 17. All of these elements are less than or greater than or equal to 17 and less than 69, and all of these elements are greater than or equal to 69. Wow, right? So this is basically an n-ary search tree. So if I had the answer 68, if I wanted to see, does this exist within this n-ary search tree, I'd go right here, and I'd go, okay, I'm greater than 17, but I am less than 69. So therefore, if it exists within this tree, it's going to be right here. There you go. So that's like the basics of a B tree. Now implemented in the HTML programming language. That's my favorite language, by the way. Let's see. Also helpful is the Intel Intrinsic Guide when looking into SIMD instructions. Note that we'll be only using AVX2 instructions here, as in we're assuming Intel, and we're not assuming less available AVX 512 instructions, in particular since my laptop doesn't have them. Dang, we should probably get Casey in at some point to explain these things again. All right, let's see. Binary search and Eytzinger layout. Ooh, a baseline will use the Rust standard library binary search implementation. Sorted vec binary search IDs equals binary. Let's see, binary search Q unwrap or else this one vals this guy. Okay, cool. I like it. I like it. The main conclusion of the the array layouts paper is that Eytzinger layout is one of the best in practice. This layout reorders the values in memory. The binary search effectively is a binary search tree on the data with as root the middle node. Then the nodes position this one right here. I'm confused. What does it mean that it reorders them? Isn't that just a sorted array? The main benefit. What is the? I guess I don't know the Eytzinger layout, and I don't want to go through that paper just to figure it out. Let's see, hold on. The binary search effectively is a binary search tree on the data. Yeah, isn't that just a binary search array? Is that all we're saying? Binary search array? Let's see. The main benefit of the Eytzinger layout is that all values needed for the first steps of the binary search are close together. Oh! It does some sort of a unique grouping with the root as the middle node. Oh, is the root the first node? Oh, interesting. Okay. We can put the root at index 1 and have two children of the node at index I are 2i and 2i plus 1. This means that we can effectively prefetch the next cache line before knowing whether we need index 2 or 2i plus 1. This can be taken a step further and prefetch the cache line containing indices 69 to 69 plus 15, which are exactly the values we needed for 4 iterations from now. For a large part, this can quite effectively hide the latency associated with traversal of a tree. Nice. Okay. Oh, very exciting. Oh, very exciting. L is the number of levels ahead to prefetch. Oh my gosh. Oh my gosh. What is this? Okay, so we got a constant sized. We got one of those const sized generics, right? So while we can shift 1 by L, multiple by the index is less than this values. Then we go in here. Holy cow, I really don't understand this thing. I really don't understand what prefetch this index even means. Okay, so this is just its position. This is just its positional offset, right? So all you're doing right here is you're just gathering. I assume prefetch index just simply accesses it. We don't have that defined, but I assume it just simply reads the value once. All right, let's see. The last few iterations don't need prefetching anymore. While index is less than this. Plus Q is greater than this length, get as U size? Huh. Okay, zeros. Trailing ones plus 1 index. Zeros, get index. Yeah, I'm not sure if I actually, honestly, I don't understand what's happening here. I'm trying to understand what this is doing, but it's doing something to the index to effectively get it into some sort of value, and then does this trailing ones business, which I'm a little bit confused by, and then sets that L size is to make a generic over arrays. Yes, I know that. This is not what I'm worried about. It's this, because this is what it's effectively doing. It's fetching out some amount out to go grab that value. Okay, well, we're just going to pretend that whatever's going on here, it's doing exactly what it said up here, which is to be able to fetch up to 16x your current index, and or to effectively fetch 4 layers further down the tree, right? If we plot these two, we see that Eytzinger layout performs as good as binary search when the array fits in the L2 cache, 256 KB. For me, the middle red line, but starts to be much better than a binary search as the array grows to be much larger than the L3 cache, 12 megabytes. In the end, Eytzinger search is around 4 times faster, which nicely corresponds to being able to prefetch 4 iterations of cache lines from memory at a time. All right, so let's see, hold on, which one? Let's see. Sorted vec binary search standard library. I wish he would have chosen slightly different colors. I'm not going to lie to you. Choosing blue and blue really make it difficult to understand the difference betwixt the two. Like, which one we talking here? Which one we talking here? Is this the blue or is that the blue? Am I too stupid to understand the difference? One will just assume that this has to be the Eytzinger ones. Obviously, the blue one. Yeah, truly here. Hold on. Maybe the problem is that I just have this thing. Here, let's turn off dark readers for a second. No, it's just blue both times. Okay, very, very difficult problem to see. I mean, this person put on blue is also worse. Yeah. So what I assume this is meaning, this is the standard library's time it takes, right? And as the array length gets larger and larger and larger into the gigabyte range, it takes longer and longer for it to be able to find it, right? Right. The latency goes up. I think that makes sense, right? Because this requires 30 accesses. As this thing grows. Okay, that makes sense. Whereas this thing prefetches some amount ahead, and somehow that makes it easier. But then it stopped being able to do that because at some point the prefetch ahead has to put in more than it can hold into the cache. if I'm reading this correct. I think so, which is actually shocking how well this does. This just goes to show that even if you are doing, this just goes to show why Big O is so broken in a practical sense, that this right here, these are the same running time, right? Whether you're right here or right here. These are the exact same Big O running time. And one would even probably say that the constant is larger here than it is right here. But because this thing takes advantage of the magic that is modern CPUs, you just get this amazing performance comparatively. Yes. I think what it says is, let's see, I think it also saying that the ordering of the memory is making a big impact on the ability to fetch, right? Yes, ordering of the memory is very, very important. And what it's saying is that the ordering and the ability for memory to be prefetched and cached so that the CPU can make really fast access is extremely important when it comes to this type of stuff, which... All right, that makes sense. Casey talked a lot about this. For all experiments, we'll make sure to allocate the tree using 2 megabyte Hugepages by default instead of the 4KB pages. This reduces pressure on the translation look-aside buffer. Oh my gosh, this is Casey. Casey used to talk about this stuff all the time with us. Okay, this reduces pressure on the translation look-aside buffer that translates virtual memory addresses to hardware memory addresses, since its internal table of pages is much smaller when using Hugepages, since it can be cached better. Okay, that makes sense. With transparent Hugepages enabled, that are, let's see, they are automatically given out whenever allocating an exact multiple of 2 megabytes. And so we always round up on the allocations for the tree to the next multiple of 2 megabytes. However, it turns out that small allocations below 32 megabytes still go on the program's heap rather than asking for the kernel for new memory pages, causing them not to actually be Hugepages. Thus, all allocations we do are actually rounded up to the next multiples of 32 megabytes instead. Okay, so it has to do 32 megabyte allocations at a time to be able to build up the array. Let's see. Also together, Hugepages sometimes makes a small difference when the data set is indeed between 1 megabyte and 32 megabytes in size. Smaller data structures don't really need Hugepages anyways. Enabling them for the Eytzinger layout, as in the plot above, also gives a significant speed up for larger sizes. Okay, let's see. A note on benchmarking. The plots have the size of the input data on the logarithmic bottom x-axis. On the top, they show the corresponding number of elements in the vector, which is 4 times less. Since each element is a U32 spanning 4 bytes, measurements are taken at values 2 to the I, 1.25, 2 to the I, 1.52 I, 1. Let's see, okay. The y-axis shows, let's see, measured time per query. In the plot above, it says latency, since the benchmark as 4Q and query n. Let's see, even then, the pipelining is out of order execution of the CPU will make it execute multiple iterations in parallel. Specifically, while it is waiting for the last cache lines of the iteration I, it can already start executing the first instruction of the next query. To measure the true latency, we would have to introduce a loop carried dependency by making query plus 1 independent on the result of query I. However, the main goal of this post is to optimize throughput, so we don't bother with that. Dang, this is just such a great, I feel like I've just been so prepared to read this by Casey. And now that we're seeing actual practical uses for it, it just feels so amazing. This is truly like the Lord's work when it comes to optimization. Thus, all plots will show the throughput of doing index query all queries. Okay, for benchmark, I'm using my laptop's i7-10750H CPU with the frequency of 2.6 gigahertz using code snippet right here. So you can go check out the code snippet if you want to go check it out, which we're not going to check it out yet. Let's see. Also relevant are the sizes of caches: 32 kilobyte L1 cache per core, 256 kilobyte L2, and 12 megabyte L3 cache shared between the physical 6 cores. Furthermore, hyperthreading is disabled. All measurements are done 5 times. The line follows the median and will show the spread of the second and fourth value. Oh, okay, so that's why there was that little blue thing right here. That's why the spread kind of existed. If you didn't notice that, there's like a little bit of a variation. This line is the median of those 5, so it's the middle element, the third best, if you will. Okay, that makes sense. All right, main memory and the caches work at a level of cache lines consisting of 64 bytes, at least on my machine, or 16 U32 values. Thus, even if you only read a single byte, if the cache line containing that byte is not yet in the L1 cache, the entire thing will be fetched from RAM or L3 or L2 into L1. Plain binary search typically uses a single value of each cache line until it gets to the end of the search, whereas the last 16 values span just 1 or 2 cache lines. Ooh, are they going to be doing some sort of weird packing stuff? Is that what we're about to hear? Are we about to hear some strange packing optimizations? Oh, baby boys. This will be great. The Eytzinger layout suffers the same problem. Even though the next cache line can be prefetched, it still only uses a single value in each. This fundamentally means that both these search schemes are using the available memory bandwidth quite inefficiently. And since most of what they are doing is waiting for memory to come through, that's not great. Also, while that's not relevant yet, when doing this with many threads in parallel or with batching, single core RAM throughput and the throughput of main memory itself becomes a bottleneck. Dang. Hold on 1 second. I'm gonna see this. The takeaway point of exercises like this is that intuition about performance in modern pipelined multi-level cache world are so good as intuitions about fluid dynamics. Use high-level abstractions, let libwriters, compilers do their job. So I don't think that's the main takeaway in my book. I think the main takeaway in my book is that memory ordering is very important. And even if you are not great, knowing that you have contiguous memory and doing operations over contiguous memory make big difference. Right? I think this is actually what makes the enshittification of the internet, is that people constantly never worry at all for anything. They're like, just don't worry about it. A libwriter will make it better. Does it? Does that actually make life better? I don't know. You use React, bro. All right, let's get back after this. Okay, all right. Let's see. The Eytzinger layout, the Eytzinger layout suffers the same problem. Even though the next cache line can be prefetched, it is still only a single value in each. This fundamentally means that both these search schemes are using the available memory bandwidth quite inefficiently. Yeah, I assume what he's trying to say, like, forgive me if I'm wrong here, I'm still trying to catch up on this, is that your cache lines are these little 64 byte cache lines, and you're storing in the 64 cache line a single U32. The rest of this is just like, that sucks, and you only get so much L1, right? L1 is not that big. So I assume what he's about to do, or he's trying to do, is that he's actually going to take this, and he's going to just power fill this bad boy with all of them so that every single one of these lines actually come through completely cached. Right, and so then he makes much more useful or much more efficient use, right? Able to shove 16 values into it, which seems like pretty exciting. Yeah, some cash money. Also, while that's not relevant yet, when doing this with many threads in parallel or batching, single core RAM throughput and throughput of main memory becomes the bottleneck. Already read that. Let's go. It would be much better if somehow we could use this information in each cache line much more efficiently. We can do that by storing our data in a different way. Instead of storing it layer by layer, so that each iteration goes into a new layer, we can store 4 layers of the tree at a time. Oh my gosh! That takes 15 values. Let's see. And could nicely be padded into a full cache line. Then, when we fetch cache lines, we can use it for 4 iterations at once. Much better! On the other hand, now that we can't prefetch upcoming cache lines in advance anymore, let's see, so that overall, the latency will be the same. But we fetch up to 4 times fewer cache lines overall, which should help throughput. Okay, good. Unfortunately, I don't have code and plots here because what I really want to focus on is the next bit. Okay, so we have 1, 2, 3, 4, 5, 6, 15. Oh, look at this. 8, 4, 12, 2, 6. Hold on. What is this one? I don't understand this layout. Other than the middle element right here, 1, which means this is 2. That means 3 should be on the other side. I am confused why 3 is here. Wait, hold on. Does that make sense? 4? Why is that? Why is that the case? Why is this the case? I'm trying to think in my head what this ordering means. All right, so this is packed Eytzinger. This is an implicit tree. S tree node. I guess I don't understand the Eytzinger layout. I'm trying to understand the Eytzinger layout. I mean, I get the 1, I get the 2. I don't understand why the 4's here and then the 8. I guess that's if you think about that, that is because it goes 1, 2, 3. So it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I think I kind of see that a little bit. Okay, I at least see the rightmost traversal in this little bit of an array. Yeah. Okay. Weird. Yeah. I should have studied up on the old Eytzinger layout, huh? The first 2 rows show how we could pack 4 layers of the Eytzinger search into a single cache line. The first follows a classic binary search layout, while the second applies the Eytzinger layout recursively. The third row shows an tree node instead. For simplicity and clarity, I'm using consecutive values, but in practice, this would be any list of sorted numbers. All right, S tier and B trees. Or S trees and B trees. We just ended with a node of 15 values that represent a height 4 search tree in which we can binary search from there. It's just a small step to S trees. B trees, but first I have to briefly mention B trees through Wikipedia. Those are the more classic dynamic variant where nodes are linked together via pointers. As Wikipedia writes, they are typically used with much larger block sizes. For example, 4KB, since files read from disk usually comes 4KB chunks. Thus, they also have much larger branching factors. Yes, B trees are typically used for like databases and disks and being able to do efficient reads from disks, because there's this whole problem where if you want to like read a very large amount if you want to search through a huge amount of data, you don't want to have to read all the data, especially from disk. So instead, you have to be able to read small bits of it to be able to know where to go next. And so that's the effective idea behind B trees, is just hyper efficient storage. S trees. We'll instead use S trees as named by Algorithmica. They are a nice middle ground between the high branching factor of B trees and the compactness of the Eytzinger layout. Instead of interpreting the 15 values as a search tree, we can also store them in a sorted way and consider them as a 16 array search tree. The 15 values simply split the data in the subtree into 16 parts, and we can do a linear scan to find which part to recurse into. But if we store 15 values, one padded in the cache line, we might as well make it 16 values and have a branching factor of 17 instead. Yes, I agree. I was a little confused why there's 16 here and there's only 15 here. I assume this is all the children. Is that what that's supposed to be? At least that's what I assume. And then, so I was wondering, why does this one have 16 versus this one doesn't have 16? I didn't quite understand that. All right. S plus trees. B trees and S trees only store each value once, either in the leaf node or in the internal node. This turns out to be somewhat annoying since we must track in which layer the result was found. To simplify this, we can store all values as a leaf to duplicate them. And duplicate them in the internal nodes. This is what we call a B plus tree or S plus tree. However, I will be lazy and just use S tree and include modification. So we have 16, 12, so everything on this side is less than 6, as we talked about. Everything in between is greater than or equal to 6, but less than 12. Everything... I believe it's greater than or equal to. Yeah, it is greater than or equal to. Right? You can see the 6 right here, the 6 right here. You can see that one right here. So there we go. All right, let's look at this for just a quick second and understand it. Blue, green, red. Blue, green, red. Oh, is this the layout? Is this what the Eytzinger layout's supposed to be? No, this is not what the Eytzinger layout's supposed to be. This is like your standard heap layout, right? Yes, that's your standard heap layout. Right. All right, so then 2, I'm trying to understand why these little highlights exist here first. Oh, this is the top level value that also appears down here. This is the duplication from here to here. Duplication, 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 duplication. Let's see, as an example of the full S plus tree that I will from now on just call S tree, on values, on 18 values with the node size of B equals 2, and branching factor of B plus 1 equals 3. Each internal node stores the smallest value in the subtree on its right. In memory, the layers are simply packed together behind each other. A full S tree can be navigated in a way similar to an Eytzinger layout. The node, not value, right, at index I has its B plus 1 child nodes at indices B plus 1 times I plus 1 plus these values, the sub values of B. Yeah. When the tree is only partially filled, the layout can waste a lot of space. Instead, we can pack the layers together by sorting the offset OL of each layer, or by storing the offset. Oh my gosh, what did I just click? Astri mentioned. Wow. Oh, look at that. We got some infinities here. All right, hold on. The children of OL plus I are then OL plus I plus B plus 1 times 1 and all this layout. So then we have 6 to infinity, infinity to infinity, which means that we have 6 and 7 right here. I don't really quite get the infinities. The full representation can be inefficient. The packed representation removes empty space and explicitly stores the offset, OL, where each layer starts. At last, we have to look at some code. Each node in the tree simply represents as a list of n equals 16 U32 values. We explicitly ask the nodes to be aligned 64-byte cache line boundaries. Oh, nice. Okay, so you do a little representation, align 64, tree node is just this many values. And this is a constant size item. Okay, that makes sense. So you're able to just pass in 16, and so you have a perfectly aligned, you have a 64-byte structure being represented here. The S tree itself is simply a list of nodes and the offsets where each layer starts. S tree B n is a vector of these tree nodes of n. Let's see, the root is at index tree offset 0. Its children start at tree offset 1, and so on. Okay. I only am partially getting this, but I think I see the general idea of just representing data in this contiguous way that allows for much better caching. So this is kind of exciting. To save some space and focus on the interesting part, to me at least, I will not show any code for constructing S trees. It's a whole bunch of uninteresting fiddling with indices, and it takes a lot of time to get right. Also, construction is not optimized at all currently. Anyways, find the code here. By the way, I'm just throwing this out there. Imagine if we would have used a Zig. I'm just throwing it out there, okay? Zig probably would have been a lot easier. Probably not a lot of fiddling. What we'll look at, well, actually, there'll be tons of fiddling. S trees sound like a nightmare to construct. Like, S trees sound nightmarish to construct. All right, search. So here's all the search stuff. It does the same offset with this whole jumping to the node. It does the whole index bidness. So it's jumping through all of these. Okay, and this is why you duplicate at the end, because then you don't have to, I assume the duplication at the end is so that, let's see, right here, the duplication at the end is such that you're not checking the keys on the way down and trying to do like a key check through here and then through here. Instead, you're just kind of leaping through. That's my assumption why. I don't really understand why you'd want to duplicate the keys. I assume it just makes it more easy to search through. All right, linear. First, let's precisely define what we want to find to do. Its input is a node with 16 sorted values and a query value q, and it should return the index of the first element that is at least q. Okay, that seems right. The results are not very impressive yet. Well, I don't know. Let's see, hold on. Let's see what it is. Sorted binary. Okay, first off, if you're that much better than a sorted binary search, that is very impressive, okay? Notice that you're not, like, look at the difference. That's very impressive, okay? When he's just like, nah, it's not that impressive. It's just like, I'm impressed. Okay, look at that. S-tree find linear, which is the one he's creating, is not as good as the Eytzinger lookup, but still very impressive. I'm jorked out of my mind right now. The initial version of our S-tree search is quite a bit slower than the Eytzinger layout, and this and following plots, old lines will be dimmed. And the best previous and best new lines slightly highlighted. Colors will be consistent from one plot to the next. Okay, auto vectorization. As it turns out, the break in code snippet 8 is really bad for performance since the branch predictor can't do a good job on it. Instead, we can count the number of values less than q and return that as the index of the first value. Okay, hold on. Let's see this. Count. Really? Search the whole dang list? Interesting. Okay, so you search the whole thing and just count instead. Okay, interesting. That's a weird, okay, interesting. Hey, boys, don't be breaking. Don't be breaking, okay? In fact, the code is not just branchless, but it's actually auto-vectorized into SIMD instructions. Well, SIMD's nuts, holy cow. Look at all those VP operations and all that. To save some space, you can find this and further results in the section figure 6 at the end of the section. This auto-vectorization version is over 2 times faster than the linear find, and now clearly beats Eytzinger layout. That's nuts. This is one of those things where it's just like I would not have thought in my head, you know what we should do? Search the whole space instead of searching up till the point and breaking from there, right? Absolutely beautiful about that. Just mind-boggling stuff. By the way, I would assume this does not work in JavaScript. So if you're taking this advice as do this in any language, you probably don't want to do that unless you can SIMDs, okay? And you should probably know what that means, and you should probably do that. You should probably know what all of that means before you do that, okay? Just throwing that out there. My guess is that people will just start writing stuff, and it just makes no sense what you're doing. All right, to save some space, you can find this and further results. I do actually want to see this. Let's show me figure 6. All right, sorted vec search. Okay, sorted vec search just goes off. Sorted vec search goes off the screen. The previous find linear goes off the screen. Eytzinger search, which was much lower, goes off the screen. And look at this. We got pop count portable. We got pop count, and that's the lowest one. Look at that. Look at that. Would you look at it? Would you look at that? The inverse throughput is 150 nanoseconds versus the 25. Crazy. Splat the query value. Dude, pop it and lock, and that's crazy. Let's see. Also relevant sizes of the cache. Let's see, hold on, we already talked about that. Uh-oh, did I lose my spot? Oh, brother, I've lost my spot. Nope, got it. First try. All right, let's see. This is auto vectorization version is over 2 times faster than the linear find and now clearly beats Eytzinger layout. We can also roll our own SIMD. The SIMD version of the original linear scan does, IDEA does 16 comparisons in parallel, converts that to a bit mask, and then counts the number of trailing zeros using portable SIMD. Oh my gosh, find counts? Find cunts? Damn. Crazy. SIMD 32. By the way, this another reason why Zig is pretty impressive is that it does actually have vectorized things built into it using compile time macros. And so a lot of the things you kind of have to do with incantations are kind of freely available in Zig, which is a super interesting. It's just Zig. Dang it. I feel like I'm becoming a Zig fan. I'm trying not to become a Zig fan. I'm trying my literal best not to become a Zig fan. And I think I'm becoming a Zig fan. Like, I'm genuinely trying not to do it, and it's happening. Zig fan. Dude, I'm a Zig fan. I'm a Zig fan. It's true for Mojo, too. Yeah, Mojo seems very interesting. Chris Latner, obviously very smart guy. Chris Latner, very smart, and I'm very curious where Mojo goes, because obviously Mojo would be the ideal language if you're doing operations that require you to constantly dip into SIMD, but you don't have the technical expertise to understand it. Meaning that everything you do can just be like, hey, calculate the best thing for me in this location and make it, and SIMD's nuts. And it just like does it every single time for you at all times. That just seems like that would be, it's like the JavaScript of SIMD, right? Yeah, exactly. All right. See, I don't understand why this versus this is better versus worse, because it's like you can't just look at a single instruction and say one is better than the other if you're a layman, right? You actually have to like know a lot of things. Now let's look at this generated code in a bit more detail. First up, why does SIMD le translate into min and compare equal? From checking the Intel Intrinsics guide, we find out that there are only signed comparisons, while our data is unsigned. For now, let's just assume that all values fit into 31 bits and are at most I32 max. There we go. This is what we're talking about. See, this is that thing that Casey showed us earlier. Remember when we did the language performance diagram? Does everyone remember the language performance diagrams? I don't know if you guys do. Press 1 if you do. But in that, Casey literally makes his version of the language performance diagram like 4x faster by just doing a couple weird operations that you would never think would be faster. Instead of doing a modulo, it does a certain set of things just because these instructions aren't available, and it just makes it like egregiously faster. And then we can transmutate our input SIMD I32H without changing its meaning. Both input values and queries are between 0 to I32 max. We'll fix this by either taking I32 input directly, or by shifting U32 values to fit into I32 range. Bada bing, bada boom. All right, let's see what just insanity happens by making this small change. I don't even know what this means, but okay, rock on. It turns out that there is only a greater than instruction in SIMD and not a greater than equal, so there is no way to avoid inverting the results. We also see that VP shuff D instruction that feels very out of place. You know what? Wouldn't have known, shuffing the D. The VP shuff D was out of place. What's happening is that while packing the results of the 16 U32 comparisons down to a single 16-bit value, data is interleaved in an unfortunate way. We also need to fix that. Here, Algorithmica takes the approach of pre-shuffling the values in each node to counter the unshuffled instruction. They also suggest that using pop count instead, which is indeed what we'll do next. Pop count. Pop count counts the number of ones, right? If I'm not mistaken, as we saw, the drawback of the trailing zero, or is it the amount of zeros? I can't remember. The drawback of trailing zero count approach is that the order of the lanes must be preserved. Instead, we'll need to simply count the number of lanes with the values less than the query. Similar to the auto vectorization SIMD before, and that the order of the lanes doesn't matter. Yeah, okay. Count ones. Count ones is pop count, right? Yeah. Yeah, we learned that from, it was like, 3 years ago, Advent of Code, where we were trying to make something really, really fast, and that really, really fast solution ended up being walking an array backwards and using pop count, if I'm not mistaken, and it just was crazy insane fast. There we go, we get a little pop count in there. Let's see. We remove whatever these two instructions are and get a pop count instead. Ideally, we would like to get move mask directly into the U16 by 16 output of the first pack instruction, vpack SSDW, to get the highest bit of each of the 16-bit values. Unfortunately, we are again let down by the AVX2. There are move mask instructions for U8, U32, and U64, but not for U16. Damn. Feels, man. Feels. Also, the VP Shuff D instruction is now provably useless, so it's slightly disappointing that the compiler didn't elide it. Time to write the SIMD by hand instead. Said literally nobody ever except for this guy. The brother is giving the SIMD a hand job over here. All right, as it turns out, by the way, that's the craziest thing I've ever said in my lifetime. I just wanted it to be known that has never been said and will probably never be said again. As it turns out, we can get away without most of the packing. Instead, we're using VP Move Mask B, Move Mask this one, on 8-bit data. We actually use it directly on the 16-bit output of the VPAC SSWD, or DW, exclamation point. I'm not going to lie to you, I'm forever lost at this point, but it seems so exciting. I'm just so excited now. Since the comparison sets each lane to all zeros or all ones, we can safely read the most significant and middle bit and divide the count by 2 at the end. All right, so we got the low, we got the high, we do a little bit of slicing, we splat that son of a B. We do a little transmute T, mask low, mask high, merge it, mask it, writing stuff by hand. Look at this, we're handing. Brother is doing some crazy stuff. Manual version of SIMD code by explicitly using the intrinsics. This is kind of ugly now, and there's a lot of transmuting, casting going on between U32, 8 and SIMD U8 and the native M256I type, but we'll have to live with it. Oh my gosh. Oh my god. Oh, I don't see in my head less of these are better, but I also don't know the throughput. Remember, we've been looking at a lot of those, and the throughput and how many operations and the amount of ports available to be able to operate can make a huge difference, but in my head this just means this is great, right? Only 5 instructions total are left, now that there are no explicit divisions by 2, since that is absorbed into the pointer arithmetic in the remainder after the function is inline. Now let's look how it work at all this. Okay, so this is the work. This is what he got, was that purple line right there. So he went from this line right here, which is just, hold on, let's go all the way back up a little bit and find that previous, let's see. Yeah, it's this one. This one ended at what, 300. So approximately 300, and now, oh my gosh. Oh, we're even doing better. Oh my gosh, he does better. So it effectively 2x the performance of find linear, if I've correctly identified that. All right, as can be seen very nicely in this plot, each single instruction that we remove gives us a small but consistent improvement in throughput. The biggest improvement comes from the last 2 steps where we indeed shave off 3 instructions. In fact, we can analyze this plot a bit more. For input up to 2 to the 6 equals 64 bytes, the performance is constant, since in this case, search tree only consists of the root node. Input up to 2 to the 10, the has 2 layers. Okay, there's a typo somewhere in here. The 3 has 2 layers, and performance is consistent. Similarly, we need latency jumping for 2 to the 14, 18, 22, and 26 each time because a new layer is added to the tree. Or rather, the jumps are at a power of the branching factor, b plus 1. Ooh, branching factor. In a way, we can also hand-wavily interpret the x-axis as time. Each time the graph jumps, the height of the jump is pretty much the same. Let's see, the time spent on processing that one extra layer of the tree. Okay, so every time you add a layer, you get yourself a little bit of issues. Once we exceed the size of the L3 cache, things slow down quickly. At that point, each extra layer of the tree adds significant amount of time since we're waiting for RAM. Since waiting for RAM is inherently slow. That phrase, that's an insane phrase, okay? That's an insane phrase for most people's daily programming experiences. That's just not what most people say. Most people do not say that phrase. On the other hand, once we hit RAM, the slowdown is more smooth rather than stepwise. This is because L3 is able to cache a fraction of the data structure, and the fraction only decreases slowly. Again, hand-wavily, we can also interpret the x-axis as a snapshot of space usage at a fixed moment in time. The first 3 layers of the tree fit in L1. The 4th and 5th layers fit into L2 and L3. Once the 3 is 6 layers deep, or once the tree, not the 3, once the tree is 6 layers deep, the reads of that layer will mostly hit RAM. Any additional layers, are sure going to RAM. Okay, that makes sense. That's why you see these steps. That's why I guess you see all these steps in each one of these. That's what he was saying by these steps, right? So this is a step, This is a step. You can see each one of the steps as it's hitting a place where it has to go and fetch out stuff. Okay, that's cool. That's pretty cool. All right, so let's optimizing the search, batching. As promised, the first improvement we'll make is batching. Instead of processing one query at a time, we can process many queries at once. This allows the CPU to work on multiple queries at the same time. And in particular, it can have multiple up to 10 to 12 in-progress requests to RAM at a time. That way, instead of waiting for a latency of 80 nanoseconds per read, we effectively wait 10 reads at the same time. Oh, damn! Lowering the amortized wait time to around 8 nanoseconds. Damn! Batching very much benefits the fact that we are using S plus tree instead of S tree, since each element is found in the last layer at the same depth, and hence the number of search steps through the tree is same at every element. See, that whole S plus, that whole like copying of an element into the tree in which it should, or the copying of the element at the bottom of the tree, I don't understand. But that seems very exciting. It just seems very exciting. Okay, here's a bunch of code that I'm probably not going to understand. Let's see the results of this. So now we're batching at different amounts, and it looks like batching effectively stops being effective right in this area. In fact, it looks like this 16 often is at the bottom. The 16 and this 128. But I mean, at this point, you probably can't get reliable. It's probably impossible to get reliable stuff. Look at that. Binary search is off the screen at 2 to the 20. His first attempts are off, or Eytzinger's is off the screen right here. These ones are off the screen. These are all off the screen. Look at that. That's crazy. L1, L2, L3 RAM. So you're in RAM land. Get ramrodded. One interesting observation is going from batch size 1 to 2 does not double the performance. I suspect this is because CPU's out-of-order execution was already deep enough to effectively execute almost 2 queries in parallel anyways. Going to batch size 4 and then 8 provides a significant speed up. Again, going to 4, the speed up is relatively a bit less than going to 8. So probably even with batch sizes of 4, the CPU is somewhat looking ahead into the next batch of 4 already. Mind blown. CPU's black magic. Throughput saturates the batch size of 16, or really around 12 already. Which corresponds to CPU having 12 line fill buffers, and thus being able to read up to 12 cache lines in parallel. Nevertheless, we'll settle on a batch size of 128, mostly because it leads to slightly cleaner plots in the remainder. It is also ever so slightly faster, probably because the constant overhead of initializing a batch is smaller when batches are larger. Okay, that makes sense. Prefetching, the CPU is already fetching multiple reads in parallel using out-of-order execution, but we can also help out a bit by doing this explicitly using prefetching. After processing a node, we determine the child, the node K, that we need to visit next, so we can directly request the node to be read from memory before continuing with the rest of the batch. Ah, yes, the old do more work, which allows you to go faster. Classic computer performance problem. This is just wild. Just wild. Greetings. Hey, Jeremy. All right. Okay, dude, this is getting just disgusting at this point. He's down to like, what, 36 batch prefetch, up to 36 nanoseconds for this. Prefetching, prefetching the cache line node for the next instruction ahead. CPU design, just pick true and false for any if statement, process further instruction back in time. Yeah, I know, it's all nutty. Look at that. You can even see each step as it's going. You can see all the steps, and then it kind of goes out of control in RAM land. Don't get caught in RAM land. We observe a few things. First, prefetching slightly slows things down while the data fits in L1 already, since in that case, the instruction doesn't do anything anyways. In L2, it makes the graph slightly more flat, indicating that already there, the latency is already a little bit of a bottleneck. In L3, this effectively gets larger, and when we get, we get a nice smooth horizontal graph until we hit RAM size. There, prefetching provides the biggest gains. Yeah, look at that, thanks gaining. So L3, it does a better job. And then RAM land. Holy cow. Pointer arithmetic. Again, oh no, here we go. It's time to look at some assembly code. Now optimize the search function itself. Results are down below in figure 9. Let's see. Upfront splat. First, we can note that the find function splats the query from U32 to SIMD32-8 on each call. It's slightly nicer, but not really faster, actually. To splat all the queries up front and then reuse those. So we're going to hit them with the splat. We're going to jump to this one. We're going to just keep on finding them splats. The assembly code for each iteration of the first loop now looks like this. Classic assembly code. I was literally just talking about the shackle earlier. Did AI find this super? No, human found this fast one. Looking at the code above, we see shackle. Oh wow, who would have guessed that that's the one I pointed out? I was like, hey, it's a shackle, and that's the one. Instruction that multiplies the given value by 64. That's because our our tree nodes are 64 bytes large, and hence to get to the ith element of the array, we need to read the byte at I times 64. For smaller element sizes, there are dedicated read instructions that inline say an index multiplication by 8. But for this article, but for the stride of 64, the compiler has to generate manual multiplications in the form of a shift. Additionally, direct pointer-based lookups can be slightly more efficient here than array indexing when doing self-tree this. We can effectively pre-compute the pointer of the tree so that ki still has to be added. So let's look at that. Okay. So we're doing. At this point, I'm lost in the sauce on whatever's happening right here because this somehow looks like we're doing even more. This is where the magic becomes so magical. Now we can avoid all the multiplications by 64 just by multiplying all ki by 64 to start with. Okay, somehow that's better. Let's go. I guess upfront multiplication is better than doing it one at a time because it's all linear, it's all contiguous. Indeed, the generated code now goes from 17 to 15 instructions, and we can see figure 9 that this gives significant speed up. Again, this whole less instruction thing, that part's always confusing to me because I know that not all instructions are simply 1, right? Some of them are 5, some of them are 2, some of them are all sorts of stuff. Where's this figure? I want to see the figure. Wait, what? It's off the screen. Brother, it's off the screen. All right. Let's see, the final version. One peculiarity about the code above is that the ANDL, this one, on line 6, the bit mask gets written there. Then in line 7, it's pop counted. Life 11 does the shell 5, i.e. multiplication by 32, which is a combination of the divide by 2 to compensate for the double pop count and the times by 64. Then it does the and 64, where the mask of negative 64, this, which ends in 6 zeros. But we can just, we just multiplied by 32. So all this does is zeroing out a single bit in case the pop count was odd. But we know for a fact that it can never be. So we don't actually need this and instruction. To avoid this, we do a little one of those to optimize optimization manually. Oh my gosh. Instead of divide by 2, you multiply by 32. What? Dude, assembly breaks my smooth brain, dude. How deep on an algorithm do you have to be to know that instead of dividing by 2, you should multiply by 32? Instead of shift left 2, you do a shift right 5. Like, that's crazy. Okay, batch final. Look at batch final. It just does better the whole way through. It does better all the way through. Goodness gracious. All right, now that we know that the first 3 levels of the graph fit into L1, so probably we can skip prefetching of those levels. Okay, nice. Skip prefetch, nice. Skip 3, look at that. Boom, even smoother. Oh my gosh, as it turns out, skipping the prefetch does not help, probably because the prefetch is cheap if the data is already available and there is a small chance that the data we need was evicted to make room for other things, in which case prefetch is still useful. Interleave. The other observation is that the first few layers of the CPU are CPU bound, while the last few layers are memory throughput bound. By merging the 2 domains, we should be able to get a higher total throughput, somewhat similar to how for a piecewise linear convex function, classic piecewise linear convex functions, when x and y are on different pieces. Thus, maybe we could process 2 batches of queries at the same time by processing layer I of one batch at the same time as layer I plus L divided by 2 of the other batch, where L is the height of the tree. I implemented this, but unfortunately the result is not faster than what we had. Or maybe we can split the work as interleaved the last level of one half with all but the last level of the other half, since the last level memory read takes most of the time. Also, that turns out slower in practice. What does give a small speed up? Processing the first 2 levels of the next batch interleaved with the last prefetch of the current batch. Still, the result is only 2 nanosecond speed up, while the code, not shown, gets significantly more messy. What does work great is interleaving all layers of the search when the tree has L layers. We can interleave L batches at a time and then process layer I of the ith in progress batch. Then we shift out the completed batch and store the answers to those queries and shift in a new batch. This way, we completely average the different workloads of all the layers and should achieve near optimal performance given the CPU's memory bandwidth to L3 and RAM. At least that's what I assume is the bottleneck now. Interleave all. So this one just is effectively a zero time performance and then pops up, and this thing is just even lower. It's on the order, look at this, it's on the order of like 27, 28 nanoseconds per check. Definitely casting a curse on your CPU. This is mage level. Okay, you have to wear an actual mage hat to be able to do this. So far, every internal node of the tree stores the minimum of the subtree on its right. Yep. Okay. It turns out somewhat inefficient when searching values that are exactly in between two subtrees. As also already suggested by Algorithmica, such as 5.5 in the case of the search tree descends into the leftmost green subtree with node 2 to 4, then goes into the rightmost red 4, 5, and then we realize 5.5 is greater than 5, and thus we need the next value in the red layer, which is stored as a single array, which is 6. The problem now is that the red tree nodes exactly correspond to cache lines, and thus the 6 will be in a new cache line that needs to be fetched from memory. Now, consider left max. Oh my gosh, we're left maxing. Left maxing. Holy cow, we're left maxing. Okay, what's going on here? Okay, so the max value's on the left, as opposed to if you look at the previous version, the values were always right stored. Okay, so we did right stored, instead now we're doing left stored. Oh my gosh. I can't even imagine this being faster, but here we go. Now, if we search for 5.5, we descend into the middle subtree rooted at 7 or 7, 9. Then we go left to 6, 7 node and end up reading 6 as the first value. Now, the search directly steers toward the node that actually contains the answer instead of the one just before. Oh my gosh, look at this. Interleave all left max. Oh, dude, left maxing even makes it somehow faster. Why? Why are we left maxing? Memory layouts. Now let's consider alternative memory layouts. So far, we're packing all layers in a forward order, but Algorithmica post actually stores them in reverse. So we'll try that too. The query code is exactly the same, but the order of the layers is already encoded into the offsets. Another potential improvement is always store the full array. This may seem very inefficient, but it is actually not bad when we make sure to use uninitialized memory. In that case, untouched memory pages will simply never be mapped, so that we waste on average only about 2 megabytes per layer on Hugepages are enabled, and 14 megabytes when there are 7 layers and the entire tree takes up 1 gigabyte. Okay, that's like nothing, right? All right. So far, we have been using packed layout. We will now try the reverse layout used by Algorithmica and the full layout that allows simple arithmetic for indexing. Yeah, see, this now we've hit a land of just insanity that just feels packed, reversed, full. This just seems crazy. All right, the benefit of storing a full array is that instead of using the offsets, we can simply compute the index in the next layer directly, as we did for the Eytzinger search. Okay, bada bam, bam, bam. All right, that looks to be the same as it was before, right? Left max, left maxin, and left max plus full seems to be the same value. As it turns out, neither of those layouts improve performance, so we will not use them going forward. Node size B equals 15. Oh my gosh. We can also try storing 15 values per node so that the branching factor is 16. This has a benefit of making multiplication B plus 1 17 so far slightly simpler, and it replaces x equals minus 4 plus x by x equals, shift 4. Oh my gosh, that's going to be huge. I don't even know. No, it doesn't look like it is huge. Well, it kind of looks like it. There's some odd initial stuff, but then I guess in RAM land it doesn't look like it matters. When the tree has up to 5 layers, the data fits into L3 cache, but using B equals 15 is indeed slightly faster when the number of layers in the tree is the same. On the other hand, the lowering branching factor of 16 requires an additional layer for smaller sizes than when using a branching factor 17. When the input is much larger than L3 cache, the speed up disappears because RAM throughput becomes the common bottleneck. Plain binary search and the Eytzinger layout have pretty much no overhead. Our S tree so far has around 1/16, 6.25% overhead. 1/17 of the values in the final layer is duplicated in the layer above, and 1/17 of those is duplicated again, and so on. A total of this, 1/16. Using node sizes 15 instead increases the overhead. Each node now has to store 15 instead of 16 elements, so that that we already have an overhead of 1/15. Oh my gosh. Furthermore, it reduces branching factor, increases duplication to 1/16 to 1/15 as well. Overall overhead is 2/15, or 13.3%, while matches the dashed blue line. Look at that. Okay, I kind of get that. That's kind of wild. Yeah. See, that was the whole duplication thing. I'm sure there's a really great reason for why that works so much better, the duplication. Why not just stop searching when you hit a value right away? I've never understood that. Right. Of all the improvements so far, only the interleaving is maybe a bit too much. It is the only method that does not work batch by batch, but really benefits from having the full input at once. And also, its code is 3 times longer than the plain batched query methods because the first and last few iterations of each loop are handled separately. Ugh. Prefix partitioning. So far we've been doing a purely comparison-based search. Now it's time for something new. Partition the input values. Oh my gosh. Map reducing. The simplest form of the idea is to simply partition the values by their top B bits into 2B parts. Then we can build 2 to the B independent search trees and search each query in one of them. Oh, we're effectively reducing the layers we're reducing the amount of layers by increasing the amount of subtrees we have. Is that effectively the idea? This saves the first 2 levels of the search, or slightly less, actually, since 2 to the 16 equals 16 to the 3. Full layout. All right. In memory, we can store these trees very similarly to the full layout we had before. The main difference that the first layers are skipped, and that now there will be padding at the end of each part. Okay. For some choices of B, it could happen that up to 15 out of 16 of each tree padding. To reduce this overhead, we attempt to shrink B while keeping the height of all trees the same. As long as all pairs of adjacent trees would fit together in the same space, we decrease B by 1. This way, all parts will be filled for at least 50% when the elements are evenly distributed. Once construction is done, the code for querying is very similar to before. We only have to start search for each query at the index of its given part, given that Q shift for some values of shift rather than the index of 0. Okay. Interesting. A lot of mapping going on. I don't even know, I don't understand what is the return value of this? Is this some sort of iterator? Oh, it does. Is it doing worse? Oh no, but it's doing better on these smaller sizes. Right? What is this? What is that? What does this even mean? We see that indeed the partitioned tree has a space overhead varying between 0 to 1, making this not useful yet in practice because, larger B reduced the height of the remaining trees, and indeed we see that queries are faster for larger B. Especially for small trees, there are significant speed up over interleaving. Somewhat surprisingly, none of the partition sizes has faster queries than interleaving for large inputs. Also important to note that while partitioning is very fast for sizes up to L1 cache, this is only possible because they have space overhead. That's the overhead, I think. Okay. Trees are red. Yeah, trees are red. It's delta compared to some line. Similar visualizations was used in the earlier figures. Yeah, I did remember seeing this in earlier figures. I just don't really understand it. And why is its performance worse in these ones? And then it looks like to be. It's hard to even say it's better at that point. Is it actually better? Oh no. Compact subtrees. Just like we used packed layout before, we can also do that now. By simply concatenating all the representations of packed subtrees, we ensure that all subtrees are still padded into the same total size, but now we only added as much padding as needed for the largest part rather than padding to full trees. Then we give each tree the same layout in memory. We'll have offsets OL of where each layer starts in the first tree, and we store the constant size of the trees. That way we can easily index each layer. Okay. The code for querying does become slightly more complicated. It's already just insane as it is. Slightly more complicated. Now we must explicitly track the part that each query belongs to and compute all indices based on the layer offset, the in-layer offset KI, and the part offset. So much is happening right now. It's like actual magic is happening. Is that better? I can't even tell if that's better at this point. It's like it's all going right in the same area. Except for this one might be like, are we getting sub 25? Sub 25? For a fixed B max memory overhead of the compact layout is small as long as the input is sufficiently large and the trees have sufficiently many layers. Thus, the tree could be practical. Unfortunately, though, querying them is slightly slower than before because we must explicitly track the part of each query. The best of both, compact first level. As we just saw, storing the trees one by one slows queries down, so we would like to avoid that. But on the other hand, the full layout can waste space. Here, we combine two ideas. We would like to store the horizontal concatenation of the packed trees, each packed to the same size, but this is complicated because then levels would have non-constant branching factor. Instead, we can fully omit the last two level subtrees from each tree and pad those subtrees that are present to full subtrees. This way, only the first level has a configurable branching factor B1, which can simply store after construction is done. This layout takes slightly more space than before because the subtrees must be full, but the overhead should typically be on the order of 1/16 for uniform data. Each tree should have greater than 9 subtrees, which only the last is not full. Okay, there's the the uncompacted ones. Here's this crazy searching. Dude, this is such a wild thing. Look at this. Dude, the bro is just trying every single method in the universe to get this sub 25. Crazy. Overlapping trees. A drawback of all the methods is that the memory usage is heavily influenced by the largest part, since all parts must be at least as large. This is especially a problem when the distribution of the part sizes is very skewed. We can avoid this by sharing storage between adjacent trees. Let SP be the number of subtrees for each part P, and S max equals max P SP. Then we can define the overlap right here, and append only B1 S max minus V of new subtrees for each new part, rather than S max, as we did before. The values for each part are then simply appended to where the previous part left off, unless the subtree is out of reach for the current part, in which case first some padding is added. This way, constructing or consecutive parts can overlap and exchange memory, and we can somewhat buffer the effect of larger parts. Oh, interesting. You're effectively shifting right. Yeah, because these ones, you'll notice these are in the middle, these are right here, and then they all go off to the right. Interesting. Man, wild. Overlapping. This guy knows B trees probably better than anybody in the universe. This guy, his name is literally B tree. When the overlap is 1, as in the above example, the nodes of the first layer each contain the maximum value of B subtrees. When the overlap is larger than 1, the nodes in the first layer would contain overlapping values. Instead, we store a single list of values, in which we can undo aligned reads to get the right slice of B values that we need. Dang. Is the goal just the goal must be to reduce this part right here. We're no longer even trying to reduce this part. We're just trying to reduce this part right here. Human data. So far, we've been testing on uniformed random data, where the largest part deviates from the mean size around square root of n. Now, let's look at some real data, K-MERS, of the human genome. DNA consists of A, C, G, T characters that can be encoded as 2 bits, so each string of K, 16 characters, defines 32-bit integer. We then look at the first n K-MERS of the human genome, starting at chromosome 1. To give an idea, the plot below shows that each K-MER of length K equals 12, how often it occurs in the full human genome. In total, there are around 3G K-MERS. Wait, is that 3G? Is this what 5G affects? There you go. Sorry, Bill Gates got me a little bit on the memory layout. Bill Gates got me on the memory layout there for a second. Hold on. We're back. We are so back. We're in the middle of some cache missing chromosomes. All right. I am curious how much faster this makes it. All right. Let's see. All right, to give an idea, the plot below shows that each K-MER length K12, let's see how often it occurs in the full human genome. In total, there are around 3G K-MERs, and also the expected count for each K-MER is around 200. But instead, we see that K-MERs that occur over 2 million times. So if we were to partition on the first 24 bits, the size of the largest part is around 2 to the negative 10 of the input, rather than 2 to the negative 24. The accumulated count are shown in orange, where we also see the number of flat regions caused by unrepresented K-MERs. Okay. We're going to get into some more. Here we go. We're going into more. We need a way to handle unbalanced partition sizes. Instead of mapping everything linearly, we can only do this by simply storing the full tree compactly as we did before, preceded by an array in blue that points to the indices of the first subtree containing elements of that part. Like the overlapping tree before, the first layer is simply a list of larger elements of all subtrees that can be indexed anywhere, potentially unaligned. Okay, let's go. Let's see. To answer a query, we first find its parts and then read the block, 16 elements, starting with the pointed to element, and then proceed as usual from the subtree onward. Dude, imagine. Oh my gosh, he's even into unsafe land. Brother's just unsafe and hard right now. Crazy. There we go. We're reading fast. Let's see, in the code, the only thing that changes compared to the previous overlapping version is that instead of computing the start index linearly and adapting the element layout accordingly, we use prefix maps to jump directly to the right place in the packed tree representation. All right, let's see, although the memory usage is now similar to the unpartitioned version, queries for large inputs are slightly slower than those previous layouts due to the additional index required. We can also, again, do the interleaving queries. These are slightly faster for small inputs and around as fast as interleaving was without the partitioning. Man, I assume this is just, I assume this equates to real dollars. Because remember this, I believe this line right here, no, not this line. That was the, let's see, where's the Eytzinger one? I believe this one right here. This is what was like the known fastest one, which is just out of this world slower comparatively. Well, this is one hell of a Monday opening article. Yeah, dude, it's crazy. On human data, we see that the partition index is a bit faster in L1 and L2 and consistently saves the time roughly one layer in L3. For larger indices, performance is still very similar to not using partitioned at all. Okay, amazing. Summary. Okay, here's the summary. Look at that poor binary search just out the window. Summary. Overall, it seems that partitioning does not provide when we already interleave queries. All right, multi-threaded comparisons. Oh, brother, we're going in on it now. Oh my gosh, we're down to like none of them. Look at that, dude. That's crazy. It's getting all the way down to like 6, 7, 8 milliseconds. When or nanoseconds, sorry. When using 6 threads, runtime goes down to 27 to 7. Wow, that's fast. Given the speedup is less than 4x, so we are now bottlenecked by total RAM throughput. And indeed, these methods are slower for a single thread, also reach near optimal throughput now. Conclusion. It's crazy that it went from that 1.1 microseconds to effectively 27 nanoseconds. And then multi-threading it, getting all the way down to like nothing. Right? Getting it all the way down to absolutely nothing. Dude, that's wild. I mean, that really is like, what? That's more than 40x. Like, this is 40x, but the other one is much less. Wow. Anyways, let's see. With interweaved query is 40x speedup. A large part of the improvement is due to batching queries and prefetching upcoming nodes. To get even higher throughput, interleaving queries at different levels helps balance the CPU-bound part of the computation with memory-bounded part, so that we get overall higher throughput using a 15 element per node instead of 16 to improve throughput somewhat, but doubles the overhead of the data structure from 16.25 to 13.3%. For inputs that fit in the L3 cache, that's fine, and speedup is worthwhile, while the larger inputs, the speed is memory bounded anyway, so there is no speedup while additional memory requirements are somewhat large. We also looked into partitioning the data by prefix. While this does give some speed up, it turns out that on skewed input data, the benefits quickly diminish since the tree either requires a lot of buffer space or else requires an additional lookup to match each part to its location in the first level of the tree. In the end, I'd say an additional complexity and dependency on the shape of the input of partitioning is not worth the speed up compared to simply using interleaved queries directly. Binary search. All methods were considered are branchless and use the exact number of iterations for each query, especially in combination with partitioning. It may be possible to handle few large parts independently from the usually smaller parts. That way we could answer most queries with slightly fewer iterations. On the other hand, the layers saved would mostly be quick lookups near the root of the tree and introduce branches to the code, possibly cause quite a bit of delay due to mispredictions. Interpolation search. As we saw the last plot above, total RAM throughput rather than per core throughput becomes a bottleneck. Once we're using multiple threads, thus, the only way to improve total query throughput is Use strictly fewer RAM accesses per query. Prefix lookups won't help, since they only replace the layers of the tree that would otherwise fit in the cache. Instead, we use interpolation search, Wikipedia, where the estimated position of query Q is linearly interpolated between known positions of surrounding elements. On random data, this only takes log n iterations rather than log n for binary search, and could save RAM accesses. On the other hand, when the data is not random, its worst case performance is n rather than statistically bounded to log n. Ooh. You don't want that. You don't want that ON. The PLA index, Abrar Medvedev, also uses a single interpolation set in precisely constructed piecewise linear approximation. The error after the approximation is determined by some global upper bound, so that the number of remaining search steps can be bounded as well. Packing data smaller. Another option is to use the RAM lookups more efficiently. Would be to pack the values into 16 bits rather than 32 bits we've been using so far, especially if we first do a 16-bit prefix lookup. We already know that those bits anyways, so it would suffice to only compare the last 16 bits of the query and values. This increases the branching factor from 17 to 33, which reduces the number of layers of the tree around 1.5 for inputs of 1 gigabyte. Another option would also suggest an ant6n on Hacker News, or by ant6n on Hacker News. Hey, thanks, Anton. Would be some kind of variable depth encoding, where the root node stores, say, the top 16 bits of every value. And as we go down the tree, we store some kind of middle 16 bits, skipping the first p bits that are shared between all elements in the bucket. Oh, some sort of like jump ahead? Is that like some sort of iteration like jump point search? Returning indices to the original data. For various applications, it may be helpful to not only return the smallest value of Q, but also the index in the original list of the sorted values. For example, when storing an array with additional data for each item, since we use S plus tree that stores all data in the bottom layer, this is mostly straightforward. The prefix map partitioned tree also natively supports this, while the other partitioned variants do not. They include buffer/padding elements in their bottom layer, and hence we do not need to store and look up position offset of each separately. It is so wild how deep you can go. Like right now, my biggest takeaway is even things like even something seemingly as simple as a B tree, you would assume that it's kind of like figured out. And this is just like going on and going on and going on and going on, just showing like how wildly amazing like research can still go. And I'm having significant skill issues right now. Let's see. We could extend the current query method to version that returns both the first value and the first value Q, so that the range positions corresponding to value Q can be determined. In practice, the easiest way to do this is by simply doubling the queries Q and Q plus 1. In this case, this will cause some CPU overhead in the initial layers, but the extra query execution will remain branch-free. When Q is not found, only occurs a few times, they will mostly fetch the same cache lines so that the memory is efficiently reused with the bandwidth. Oh, nice. Oh, that makes sense. Oh, that's cool. In practice, though, this seems only around 20% faster per individual query for 4 gigabyte input, so around 60% slower for a range of single query. For small inputs, the speed up is less, and sometimes querying ranges is even more than twice as slow for individual random queries. Sorting queries. Another thing we did not at all consider so far, but was brought up by Orpel on Hacker News, is to batch queries. If we assume for the moment that the queries are sorted, we know that we have a maximal possible reusing of all nodes. So they all need to be fetched from memory only once. If the number of queries is large, say at least one, n divided by 16, then many nodes at the last level will have more than one query hitting them, and fetching them only once will reduce memory pressure. Similar, if we have at least around n divided by 256 queries, we can avoid prefetching before last layer nodes multiple times. In practice, I'm not quite sure how much time the sorting of the queries would take, but something simple would be to do 1 or 2 rounds of 8-bit radix sort. So we sort 256, 2 to the 16, or 65536 parts, and we skip the first 2 or 4 first layers of search. I don't know how that actually works, but that seems interesting Seems neat. Suffix array searching. The next step of this project is to integrate this into a fast suffix array search scheme. The idea is to build this S tree on, say, every fourth suffix, and then use the first 32 bits, or maybe 64, of each suffix as the value of the S tree. Given a query, we can then quickly determine the range corresponding to its first 32 bits, and the binary search only in the likely small remaining range to determine the final slice of the suffix array that corresponds to the query. And then a bunch of references. This is crazy. Wow. Absolutely insane research. You know, my brain too small. My brain too small too. It's very interesting though. It's very interesting all the things that can be done. I think all this shows me is just that computer science is an infinite skill gap. You can keep going and you can keep on getting better and better to the point where whatever you're working on, there's so much more that you can go. You know, this guy is a wizard. But here's the best part is that just because he's good in one thing doesn't mean he's good in all things. And so that's actually kind of cool in the sense that you can pick a topic and become really good at a specific topic. Yeah, he's working on his PhD in bioinformatics, right? So it's really cool. And so it's there's something magical about becoming an expert in something. And so there's just really it makes me excited more than anything else. And for the last couple years, I've been trying to decide what is the next thing I want to become an expert on. And I've been kind of playing around a whole bunch with just different languages, kind of really trying to figure out what's the next place I really want to get good at. And I can slowly feel like the place that I want to go and expertise out is probably going to end up being Zig. I think it's probably the nicest. I have options to do it either in Odin, to do it in Zig, or to do it in J. And J's pretty interesting. Odin's really interesting. And Zig's really interesting, but Zig just seems like it has the most amount of ability to get really interesting, right? Well, I wanted to do, like I said, I was going to do 1 year Golang. For those that are pivoting again, no, I said I was going to do 1 year of Golang, and we did. 2024 was all Golang. The only thing is that I did take a 1 month detour and did Zig, and I really enjoyed my time in Zig. So I was like, okay, that was really fun. That was in 2024, I was looking ahead to what I wanted to do in 2025. And in 2025, I'm pretty much stuck between doing stuff in Elixir or doing stuff in Zig. I either want to go functional, which is going to be OCaml or Elixir, or I want to go manual memory, which is going to be something like Zig, Odin, or Jai, or J. I don't know how to say it. Jai or J. I'm not sure which one to say, right? And so it's I'm kind of in this world right now. I've done C++. I've done C and C++ professionally. I don't want to do that again. All right. I've already done it. I don't want to do it again. All right. I don't want to, you went deep inside it, right? And so it's I feel but anyways, the reason why I say all these things is to encourage you, there's so much space that you can infinitely extend yourself on, right? Programming doesn't just simply have to be you putting boxes on the screen and making them colorful and making them pretty. And then taking that, and when it's clicked, it goes through some arbitrarily complex, abstracted kind of requesting algorithm, which then goes on and goes over here onto the back end, which then goes in here and calls out a database or Redis or whatever caching layer, and then returns the response, and you update this to a check mark. It doesn't have to be the end of programming. You can keep on going, right? You can keep on going deeper and deeper and deeper, and it does not have to end with a little bit of CRUD app, right? Somebody has to write the DB in the first place. But the thing is what you do professionally versus what you do personally, they can be different too. Because eventually, if you go long enough in the personal realm and you find the thing you really like to do and you really want to keep on building stuff with it, you will find that you get really, really good at it. And eventually, your personal life becomes your professional life. And this is where you achieve the quote unquote dream, which is amazing. How about you explore hardware? I did a lot of hardware at one point in my life. I did it professionally in C. I wrote network drivers. I wrote flash drivers. I wrote planetary pancake motor algorithms. I helped effectively the government be able to create an invisible fence in which uses LiDAR to be able to tell if there's been volumetric changes within 200 meters, and then point a camera at it and then take video of that and send it back. And then I created a network of nodes. This is right out of college, by the way. Create a network of nodes that would like kind of mesh forward this to a command center. And so it would just be able to figure out all those things. This is kind of why I got into network stuff to begin with. Network stuff has always been fairly fun because creating your own network protocol is just cool. It's just fun. It's just a good time. But that was a lot of fun. And so I don't really want to do, but I don't really want to keep on doing, what's it called? I don't really want to keep doing hardware. I think hardware is neat, but it's like neat as in hobby. It's not neat as in professional for me, right? If that makes sense. Like, it's not something I want to do all the time at all points in my life. I really like building out dumb programs. I really want to keep on going in this, and I'm going to finish out the Rust version of this program, and I'm going to make this. I am finishing out the last version of this, and this is going to be my last rewrite it in Rust. Note, this is the last rear, right? This is my last rear. I'm just over it. Right. Anyways, there you go. That's all I wanted to say. This is great. This is fantastic, and I hopefully this is more of an encouragement note at the end. Right. There you go. The name is the Primogen.